Hello everyone, let's talk about another medium level problem on Leetcode today, kth smallest prime fraction, Leetcode 786. In this we are given an sorted integer array containing a number 1 and also other prime numbers remaining in the array, and all the integers in the array are unique. We are also given an integer k, so we have to return the kth smallest fraction considered. A fraction can be calculated like here they give the way we can calculate the fractions. So we choose any indices I uh, between 0 and array length, and j between I and array length, and we calculate it by using array I by array j. So we will array j will never be 0 because it will be either 1 or more than 1, whichever prime values there are in the array. So we have to return the kth smallest fraction. So let's look at the example. So in the first example that we have, it is we are given like number 1, right? 2, 3, 5. So k is equal to 3. So what are the available fractions? They have given like 1 by 5, 1 by 3, 2 by 5, 1 by 2, 3 by 5, and 2 by 3. And if we say k equal to 3, 2 by 5 should be the answer. So they have given the fraction already in the sorted order. Similarly, in 1 comma 7 we will only have one fraction, which is 1 by 7, and they have given k equal to 1, so that will be our answer. So basically we are returning a pair which will denote the fraction where the first value is numerator and second value is denominator. Now let's jump into the solution space. So there are multiple ways we can solve this problem. One of the naive approach can be that we calculate all the fractions. So for example, we loop onto the array, say from I equal to 0 to n minus 1, that is the last element, and j equal to I plus 1 to the last element. So basically we can calculate create the fractions like 1 by 2, 1 by 3, 1 by 5, right? Then we will do the same thing for 2. It will be 2 by 3, 2 by 5, and then eventually 3 by 5, right? So these are the fractions available for us. Now what we will do is we will sort them and eventually and return the and also store the pairs here, like pair of it will map to 1 by 2 will map to 1 comma 2, right? Similarly 1 by 3 will be mapped to 1 comma 3. So 1 by 3, by the way, will be equal to 0.33. 1 by 2 will be equal to 0.5. So similarly we will just now sort it based on the fractional value that we got and return the kth element. So if we think about the time complexity here, it will take O of n square, right? N square log n, because to create all of these fractions, that will take O of n square time. And then once we create the fractions, we sort them. So that will take O of n square log n time. So overall time complexity will be O of n square log n, and space complexity will be also O of n square, because we have to store this as a pair, right? We are storing the fraction as well as the values that we have to return from it. So this is one approach. Another approach can be that what we can do is we can actually like create the fractions again, like we just now discussed, and like for example, it will be 1 by 2, 1 by 3, 1 by 4, and sorry, 1 by 5, not 1 by 4, sorry. And then we have 2 by 3, 2 by 5, and then 3 by 5, right? So these are the fractions. So we will add them to the min heap and poll them k times. So the kth value that we will get will be our answer, and that will again take O of what you say n square log n time, because what we will be doing is like O of n square time will be needed to create those fractions and adding them to the heap, and O of k log n square time will be taken, because we the heap will have n square elements in it. and we have to poll it k times, so that will take this much amount of time. And in terms of space complexity, we will be again using O of n square. So this is another acceptable solution. Maybe what we can do is like we can just jump into the code, and then we will talk about the efficient solution afterwards. Yeah. So for this, what we will need is like we can create a class called fraction, right? And one value will be fraction, another value will be int numerator and int denominator, because those are the value we will also need to store. And we can start. We can create a priority. Like in Java, we use a priority queue for creating either min heap or max heap. So what we will do is we will need a priority queue of fractional value, and we can call it min heap, right? And what we have to also do is we have to create the min heap, right? So we will say that double dot comparing, right? We can use this method, and we can say yeah, if we pass a comma b in terms of comparator, then what we will need is we will need to use a dot frac comma b dot frac, right? So this is one thing we have to do. So now that we have created this min heap, we can start looping into the onto the array. Let me also create a variable called length of the array. I less than n I plus plus, right? And j will be um, j less than n minus 1 j plus plus. And now that we have it, by the way, if you want to jump onto the more efficient solution, please skip this section. And now we can just add it to the heap, all the values we have seen so far. So if we have min heap dot add, we need to create a new fractional class, and we will pass value as, so we can compare double d is equal to double. So what we need is uh, yeah, what we will need is array I by array j, right? And we will add this double value. We will add array I, and we will also add array j. That's it. So now we have it. We will I also need to create the constructor in this class, right? Double d double frac int nr int dr, right? And we can say this dot frac is equal to frac, this dot nr is equal to nr, and this dot dr is equal to dr. And now what we will do is we will just start what you call adding the yeah, once we have added them to heap, we will start polling them. So we will say int I equal to 0, I less than k minus 1, I plus plus, and we can just say min heap dot poll. We don't have to store this value because we are just letting the first k minus value pass away. We just care about the kth value when we pull it out. So now we will say frac answer is equal to min heap dot poll. So now this will be the kth value, and what we will return is pair of answer, right? We will need the new integer, and we will be returning answer 0 comma answer 1, right? Oh, sorry, answer dot numerator and answer dot denominator, and that should do it. Let's see if this works out. Let's run the code. I hope there are no compilation issues. Oh, there are so many. Why? So it says, ah, I should have written for. Let's, and are there any other errors? I hope no, but let's see. My bad. And oh, I forgot the semicolon as well. I hope, I mean, I wish they can give the all the compilation error in one go. So what's the error now? It says that double dot compare, maybe double dot compare, not comparing. Let's run it. Awesome. So now I get the compilation issue. So it says expected answer is 2 by 5, but I'm giving 2 by 3. Let's revisit the code. Most probably, yeah, I think looks like this is the issue. I should have been doing j less than n, not j less than n minus 1. I think it's a typo. So let's run this code again. Yeah, let's submit this code. Cool. So this beats only 5% of the Java programmers. Of course, I don't believe in these numbers because they can vary from 5% to 50%, but this is definitely a slow code, and we know it, right? Why? Let's think about it. So when we go into the description, they said that this array is already sorted. So when I create the max, when I create all these pairs or the fractions like this, actually I'm not taking care of what you say this property that they have already given, that the array is already sorted. So can I use it somehow to efficiently calculate the what you say heap variables rather than just calculating all the fractions and selecting the key out of them? And the answer is yes. So how about we do something like this, that we can say, so we have all these numbers, right? So what if we just start with one fraction, because we can't use like for the creating this fraction in this particular problem, we can't use the same numerator and denominator. But what if we do this, that we take three numerators, 1, 2 and 3, right? And create the fraction with just the biggest what you say um, biggest denominator we have. So in this case 5. So we will take, I'm talking about example 1. So we take 1 by 5, 2 by 5 and 3 by 5 and just add it to the heap, right? So in this case, do is this sufficient to actually find the next largest or next larger fraction till we have touched k? And the answer is yes. So what we can do is, like, we can keep the numerators same, but if and we can, what we can do is, like, we can use like a indirectly like a two-pointer approach here. Like we have these four values, right? So we can start the denominator being here and initial numerator being here for all the values, right? For this one, for this numerator and this one, and we just add 1 by 5, 2 by 5 and 3 by 5 to the heap. So this is the minimum denominator numerator we will get. Why? Because we are dividing all the numerators by the maximum value we have in the array, right? So once we have done it, we are actually smartly using the sorting property of the array. Now when we poll out 1 by 5, suppose we didn't find k equal to, like in this case, k equal to 3, and when we return the answer, maybe 2 by 5 is suffice, right? Or and we find the answer. But let's see how. So what we will do is, like, we will say, okay, 1 by 5 we pull out of the heap. So what's the next bigger fraction we can get? So we can get 1 by 3, right? Because we will start decrementing the denominator. So 5 was the biggest denominator for numerator 1. What is the second highest what you say fraction? Yeah, what is the next highest fraction we can get with numerator 1? That is 1 by 3, because we will choose the next denominator basically. So we will add 1 by 3 to the heap, 2 by 5 to the heap, and 3 by 5 were already to the heap, were already in the heap, right? So now, so which is bigger? So this is 0.33, this is 0.4, and this is 0.6, right? So when we once we poll out, then we again poll out 1 by 3. And now when we poll out 1 by 3, what is the next bigger fraction we can get with the numerator 1? It is 1 by 2, because that's 2 is the next smaller denominator after 3. So now we add 0.5, and now again k is equal to now 1, because we have polled two elements so far. Now we add, now we again pull out k. Sorry, we pull out the next bigger fraction, which is or the smallest fraction in the heap so far, that is 0.4, because this one, the value we added was 0.5, which is more than 0.4, and also 0.6 was already more than 0.4. So we pull this out, and now k is equal to 0. Aka, we have found actually the solution, and we return this. So I hope you understand the beauty of the solution. We have to actually use the sorting property. And in this case, what will be the time complexity? The time complexity will be O of n to build this initial heap, right? And then every time we pull out the element or remove the minimum from the heap, that takes log of n time. And because we have to do it k times, it will become k log n. So it will be O of n plus k log n, right? And we can argue that k at maximum can be equal to n, right? So or in the multiple of n. So we can have what you say, n plus n log n in a way, right? And in terms of space complexity, again it's O of n, because we are storing n minus 1 fractions in the heap at a given time, and hopefully that actually makes the space complexity way better than we had in the previous solution, which was O of n square, and also the time complexity way better. Now let's jump into the code part again. So also, yeah, one more thing is, like, we are using a double dot compare here, right? So this is one thing, but what we can also do is, like, instead of using double dot compare, suppose we had two numerators, nr0 and dr0, and we had another numerator nr1 and dr1. So earlier we were just literally using the fractional value of the double. This is one approach. Another smart approach that we can use is, we can say, if nr0 dr0 is more than, say, nr1 dr1, then nr1 by dr1, then in this case we know that nr numerator 0 into denominator of 1 should be more than numerator of 1 into denominator of 0. So we can actually also build a min heap based on this, and we don't have to calculate the double value again and again. So that will also make our algorithm a bit faster. Now let's jump into the code part. Now we will reuse the min heap, but instead of storing the frac object, we will be storing the integer pair of numerator and denominator values. Or the indices, right? And then what we will do is numerator index and the denominator index, and for each pair of numerator and denominator index we will be comparing. So we can do either integer dot compare. So we can either do this, uh, right? In Java, if we have two integers x and y, we can say x minus y. So if I as a comparator value, so if it's less than 0, that means x is less than y. If it's more than 0, that means x is greater than y. And if it is equal to 0, then yeah, we know that those two numbers are equal. So we can do this. So air of a0, that is numerator in first pair, into air what you say, b 0 b1, right? We need the denominator of the second pair, minus air a1, that is numerator, sorry, denominator of the second pair, into sorry, denominator of the first pair, and into numerator of the second pair. So once we have it, yeah, either we can do this like we said, or we can just simply use integer.compare if it's easier to read for you. Yeah. And just add one more parenthesis. Yeah. So we once we created this parenthesis, once we created this priority queue or min heap, what we will do is we will start looping onto the array. But instead of adding all the elements now, we will be just adding the numerator and the denominator index. So we will say min heap dot add I and n minus 1, right? And the reason is like I is the current numerator index and n minus 1 is the last or the highest value we have in the array as a denominator. And also we have to do it till n minus 1. Reason being numerator and denominator values cannot be same. So the indices should also not be same. And now we will start polling out the k minus 1 elements from heap and then eventually poll out the kth element. But instead of just polling and not doing anything with the k minus 1 elements, we have to poll and update the new element or add the new element into the what you say min heap with the reduced denominator value, right? So what we will do is like we will get the current fraction that we have. Then we will get the numerator index, which is frac 0, right? And we will also get the denominator index, which is frac 1. Once we have it, we will check if NR index is what you say, yeah, sorry, the dridx minus 1, because denominator will always be on the right and numerator will be on the left because denominator is bigger. And what we have to do is like if it's more than what you say numerator index, then only we will add it to the queue, because if they become equal or if what you say it's more the denominator is less than numerator, that means we don't have to add the fraction anymore, right? We need the fractions, not the values which are more than 1 basically or equal to 1. As denominator and numerator cannot be same, then only we will add it to the min heap. So we will add min heap dot add numerator index, and as we talked about, we will reduce the denominator now. That means we are adding a bigger fraction now to the min heap. And once this is done, I think we will come out of the heap again, reuse the same variable numerator index and denominator index, right? But instead of using it on the fraction that we created earlier, we will just use it for the answer, because we have pulled out k minus 1 and this is the kth element. And in terms of answer, we will return array of nridx, because we need to return the values, not the indexes or indices. So awesome. So I think once this is done, now we will just get rid of this fractional class as well and now run this code. Hopefully again, I hope there are no compilation issues, but there are. So it says that we can't add a pair like this, so we need to add new int new int array, right, to the heap, and similarly I have to do the same thing here. Now let's run the code and see if it works now. Awesome. So let's now submit this code. Cool. So this time it's way faster. It's around 200 milliseconds for the same code. So I hope you enjoyed the solution, and if it helped you, please do like and subscribe. I have added the code link and the problem link into the video description with a similar explanation, those who want to read and understand. So thanks again and have a nice time.